Imagine the night sky, just completely still, silent. That endless tapestry of stars. Then, suddenly, this invisible energy, it just races across the cosmos. It's not light, it's not sound, it's like the universe itself is rippling. And on November 23rd, 2023, these ripples, well, they told us an incredible story, something unprecedented. GW231123, it's the most massive black hole merger ever detected.
Yeah.
And honestly, this event sort of defies everything astrophysicists thought they knew. So today, we're going deep into the science, the mystery, and the really revolutionary implications of this whole thing. Okay, let's unpack this. So maybe start with the basics. What exactly did the observatories like LIGO, Virgo, KAGRA, what did they actually pick up that day? What was GW231123?
Right. Well, what they detected was, frankly, wild. You had two black holes. One was about 100 times the mass of our sun.
Okay, 100 solar masses, big.
Yeah, big. But the other one,
Yeah.
even larger, around 140 solar masses. And they were locked in this final cosmic dance, spiraling into each other. But the really astounding part, the thing that made everyone sit up, was the result. A single final black hole formed from that merger, weighing in at roughly 225 solar masses.
225 times the mass of the sun. That's enormous.
It is. And the initial shock, you could almost feel it ripple through the community. This wasn't just another black hole merger. It was a monster, really, born from two other, well, near monsters. And nobody expected anything quite this heavy. What's truly fascinating here is the sheer mass, that 225 solar mass remnant. It lands smack bang in the middle of what we call the forbidden mass gap.
The forbidden mass gap. Okay, that sounds intriguing.
It is. It's this theoretical range based on how we understand massive stars dying, where black holes at this size, well, they just shouldn't form directly from a single star's collapse.
Right, okay, so here's where it gets really interesting then. Because the standard thinking, the theory we've worked with for decades, says that stars between, about 60 and 120 solar masses, they're supposed to go out in this incredibly violent explosion, right? A pair instability supernova.
Exactly. It's a specific type of supernova.
And the way that works, it's so energetic, it's meant to completely blow the star apart, leaving nothing behind. No black hole, no neutron star, zero remnant.
That's the prediction, yes. Total disruption.
So this black hole, the remnant of GW231123, it's like a ghost that shouldn't be walking the Earth, right? It shouldn't exist according to that model. So how are scientists even starting to think about how something like this could form? It seems like a complete contradiction.
That is the big question.
Yeah.
It's really forcing us to look hard at some fundamental assumptions about stellar evolution and death. Right now, there are, broadly speaking, two main ideas, two pathways people are exploring. One is something called hierarchical mergers. The idea is that maybe smaller black holes merge first, creating bigger ones. Then those bigger ones merge again, and you sort of build up mass incrementally over time, step by step.
Ah, okay. Building blocks.
Kind of, yeah. The other possibility, which is maybe even more exciting or perhaps unsettling depending on your view, is that there's some unknown physics involved. Something missing from our current understanding of how stars work, or maybe even how gravity works in these extreme conditions.
Unknown physics. Wow, okay, so if this thing exists, despite the theories, how do we even sense it? How do you hear something like two black holes crashing together billions of light years away?
Yeah, it's incredible technology. It comes down to detecting those gravitational waves you mentioned earlier, those ripples in space-time itself.
Right.
We use this amazing global network of detectors. There are the two LIGO sites in the U.S., Virgo in Italy, and KAGRA in Japan, which is coming more online.
A triple network, essentially.
Or even more, yeah. And the key is triangulation. Because the gravitational wave travels at the speed of light, it hits each detector at a slightly different time. Nanoseconds difference.
Tiny differences.
Extremely tiny.
Yeah.
But by measuring those arrival time differences very, very precisely, we can figure out where in the sky the wave came from. It's like using the entire Earth as a giant listening device.
That's amazing. And the signal itself from GW231123, I read it, was quite remarkable, something like 2.2 seconds long.
It was. And that 2.2 seconds, that might sound short, but for a gravitational wave signal from merging black holes, especially massive ones, that's actually quite long.
Okay.
It captured the whole final dance, the merger, and even the ring down of the new black hole settling. And the signal was strong, very clear.
So for just over 2 seconds, the universe was basically singing this song of, well, destruction and creation.
That's a good way to put it. It was a powerful signal. And yes, our instruments were finally sensitive enough to pick it up clearly.
Must have been quite a moment for the teams.
Oh, absolutely. When an alert like that comes through, with those kinds of estimated masses, there's this immediate buzz. Could this be real? Is it that massive? Because you have to understand, when these black holes spiral in, they're warping space-time like crazy around them.
Right.
That dance causes them to lose energy through gravitational waves, making them spiral faster and faster.
Towards the inevitable collision.
Precisely. And then after they merge, the new combined black hole isn't perfectly spherical right away. It sort of wobbles like a struck bell and settles down. That's the ring down phase. And it emits its own characteristic gravitational waves. It's the echo of the collision.
A gravitational echo. Love that. So the really big question then, the one probably buzzing around labs everywhere, did this event finally break Einstein's theory of general relativity? Did we find the limit?
Yeah, that's always the hope, isn't it? Finding the crack in Einstein's theory. But no, general relativity, it remarkably still holds up. The signal we saw, its shape, its evolution, is consistent with the predictions of GR for merging black holes of these masses.
Okay, so Einstein survives another round.
He does. But you could say the theory is definitely sweating a bit.
How so?
Well, while GR itself isn't broken by this, an event this extreme, with these masses, pushes our application of GR and our astrophysical models based on it right to the edge. It's testing the limits of our ability to predict what happens in these really, really strong gravity regimes. And it definitely raises questions.
Like what sort of questions?
This raises an important question. How does matter, or in this case, the singularity within a black hole, actually behave under such immense gravity? We treat them as points in GR, but reality might be more complex. And looking forward, events like this, especially if we find more, could potentially become laboratories for testing ideas beyond standard GR, maybe even hints of quantum gravity, once our detectors get even more sensitive.
Right, so it's less about GR being wrong, more about the implications for everything else built upon it, like our understanding of stars themselves.
Exactly. This collision wasn't just some random cosmic smash-up. You could see it as a message from the universe saying, hey, your models, they might need an upgrade.
Okay, so how does this change how we think stars might evolve?
Well, it suggests that maybe the standard picture isn't the whole story, especially in certain environments. Perhaps stars in really dense cosmic neighborhoods, like the centers of galaxies or globular clusters, evolve differently. Maybe they hold on to more mass or merge before they die.
And you mentioned metallicity before. How does that play in?
Right, metallicity, the amount of heavier elements in a star, plays a huge role. Stars with lower metallicity, like those common in the early universe, tend to lose less mass through stellar winds during their lives.
Ah, so they can stay heavier.
Potentially, yes, which could make it easier for them to eventually form more massive black holes. This event also makes us think more seriously about other possibilities, like maybe some truly giant stars can collapse directly into a black hole without that pair instability supernova ever happening. Or perhaps these giants are the result of multiple generations of star formation and mergers within dense clusters.
It really makes you wonder, doesn't it? How many more of these forbidden giants are lurking out there that we just haven't detected yet?
That's the exciting part. We're only just scratching the surface with gravitational wave astronomy. This event could be the first hint of a whole population of unexpectedly massive black holes.
So let's circle back to one of the main explanations you mentioned, hierarchical mergers. This idea of black holes building up like cosmic Lego bricks.
Yeah, that's a great analogy. The hierarchical merger hypothesis is definitely one of the leading contenders to explain things like GW231123, especially given that forbidden mass gap problem.
So the idea is you start with smaller black holes, say from regular star collapses.
Right, maybe 10, 20, 30 solar masses. Common stuff.
And then in really crowded places, they find each other and merge.
Exactly. Think about the core of a globular cluster, these ancient, densely packed balls of stars, or the very center of a galaxy near the supermassive black hole.
Lots of gravitational interactions.
A lot of interactions. Black holes can sink towards the center due to dynamical friction, increasing their chances of encountering each other, forming binaries, and eventually merging. So a 30 merges with a 30, maybe you get something around 60, minus some energy lost to waves. Then maybe that finds another one.
And slowly, or maybe not so slowly, you climb the mass ladder.
Precisely. You build up. And this process could potentially create black holes in that pair instability mass gap, and maybe even push toward the sizes we saw in GW231123.
Does this also help explain those intermediate mass black holes people have been searching for? The ones between stellar mass and supermassive?
It absolutely could. Hierarchical mergers provide a very natural pathway to creating those middleweight black holes, which have been quite elusive observationally. So finding massive stellar mergers like this adds weight to that whole mechanism being important in the universe.
Okay, so the hunt is definitely on for more events like this, and our ability to listen is improving, right? What's next for gravitational wave detection?
Oh, things are moving fast. LIGO India is set to join the network soon, which will significantly improve our ability to pinpoint sources on the sky. Better triangulation.
More ears listening.
Exactly. And then looking further ahead, we have the next generation of detectors being planned and designed. Things like the Cosmic Explorer in the US and the Einstein telescope in Europe.
What will they be able to do?
These will be much larger, much more sensitive instruments. Think 10 times the sensitivity or more.
Wow. What does that mean in practice?
It means we'll be able to detect fainter signals, which means signals from much, much further away, deeper into cosmic history. We'll be able to see mergers happening across almost the entire observable universe. Plus, the improved sensitivity means we'll get much cleaner signals, allowing for even more precise tests of general relativity, and potentially uncovering finer details about the black holes themselves, like their spins. And AI is playing a bigger role too, helping us sift through the data and analyze complex waveforms faster.
So tomorrow's detectors won't just, hear the black holes
You
merging.
might be able to map out their family trees, in a sense. By seeing populations of black holes at different cosmic times, we can start to piece together the entire history of how these objects form and grow.
That sounds incredibly exciting. We're really moving from just detecting these things to doing detailed astronomy with them.
It's a whole new era. Gravitational wave astronomy is complementing traditional telescope observations in ways we only dreamed of a decade ago. The potential for discovery is just immense.
So wrapping this up, GW231123 clearly wasn't just another blip on the detectors. It feels like a truly pivotal event.
I think that's fair to say, yes.
It really forced us, or is forcing us, to question some deep assumptions about how the most massive stars live and die and how black holes grow. It showed us that even Einstein's theory, as robust as it is, gets pushed into interesting territory by the real universe. So, what does this all mean for you, listening? I think what GW231123 really hammers home is that the cosmic rulebook, the one we thought we understood pretty well for star death and black hole birth, might need some serious revisions, maybe even a radical rewrite. This isn't just a scientific curiosity, it's kind of a profound reminder that the universe is, well, far wilder, more creative, and maybe more destructive than we ever imagined. It's constantly challenging our neat little boxes of understanding reality, which leads to that final thought. What other forbidden giants are out there? What other rules are waiting to be broken? If GW231123 is just the start of a new chapter, well, the next page could genuinely change everything we thought we knew. Stay curious. Stay cosmic.